Hello students, let us proceed with the topic effective aperture or capture area or effective area. Now let us consider an antenna. So this is an antenna, okay, and we are going to find the effective area. This is the area which it extracts the electromagnetic energy. The wave is incident here, so it is extracting the electromagnetic energy from this traveling electromagnetic wave, and that area is called as the effective area. But mathematically defining this equation, A is defined as a ratio of power received at the antenna load terminal with respect to the pointing vector of the incident wave. This is the incident wave. So AE is equal to W divided by P, or W is equal to AE into P. It is a mathematical relation where W is power received, AE is effective area, P the pointing vector of the incident plane wave. Okay, now we have seen a receiving dipole antenna with a terminating load impedance. This is the Thevenin equivalent. What do we mean by the Thevenin equivalent? We are replacing the antenna by a voltage source along with the antenna impedance. So this is Thevenin voltage, equivalent voltage, Thevenin equivalent impedance. For what purpose are we doing this? Now, as we have spoken, an aperture or the area we are going to calculate is defined in terms of W by P. Here I would like to make a concept clear. The term aperture in antenna is nothing but the diaphragm in physics, an iris, an opening in your digital image processing, your window in digital signal processing, a slot in antenna. So every word is similar, but depending on the concept where it is being applied. So here it is being with respect to the area of the opening. So effective aperture equal to W by P. Now I am assuming the terminal current in the antenna to be IRMS and the load resistance to be RL, such that W is equal to IRMS square into RL. But already we know that AE is equal to W by P. So AE can be rewritten as, I am substituting the W value, IRMS square into RL divided by P. Name this as equation number 2. Now, as we have spoken, the antenna is extracting energy from the incident waves and it is delivering the same to the load impedance. So by equivalence, I can transfer this antenna into a Thevenin equivalent circuit with an equivalent Thevenin voltage of V and equivalent Thevenin impedance of ZA. Now, how to define I? I is nothing but V by Z, a known equation. Here IRMS is equal to equivalent voltage divided by the equivalent impedance. IRMS equal to V divided by ZL plus ZA. In the diagram very clearly we have seen I is a current flowing through this antenna. So the same current is assumed to be flowing through this equivalent circuit, which is an RMS value. So IRMS is through this circuit is equal to V divided by ZL plus ZA. This is what we are choosing as the IRMS equation. I am defining ZL to be a load impedance, which is a complex impedance, RL plus JXL, and ZA to be antenna impedance, which is equal to RA plus JXA. But RA is defined as the sum of radiation resistance and loss resistance, which is RR plus RL. So I can replace ZA by RR plus RL in the place of RA plus JXA. Name these equations as 3, 4 and 5. Now we are moving on to substitution of equation 4 and 5 in 3. So IRMS becomes equal to V by, in the place of ZL and ZA I have substituted RL plus JXL, RA plus JXA. Again in the place of RA we are replacing RR plus RL. We are modifying this equation and then substitute this equation 6 in 2. We know the basic equation of AE is equal to IRMS square into RL divided by P is equation number 2. So after finding out IRMS value, I am substituting in the equation for AE to get the final expression of AE is equal to V square into RL. This equation I have substituted here. So it is V square into RL divided by RL plus RR plus RL the whole square plus XL plus XA the whole square into P. This is the final equation. So here I have found the magnitude from this equation. It is understood. So the equation number 7 is the final equation of effective aperture, and according to maximum power transfer theorem, maximum power is transferred from the antenna to the load at what conditions? The condition number 1 is XL is equal to minus XA, and condition number 2 is RL equal to RA. So I am replacing XL equal to XA. So this term is becoming 0. RL equal to RA. This is RA. So 2RL square. Upon simplification, it is defined by V square divided by 4RL into P is equal to AE. Now, with this equation, I am defining the maximum effective aperture by making RL term already we know which is equal to RA. If this loss resistance small RL is equal to 0, automatically RA becomes equal to RR is called as the maximum effective aperture. So I should remember the condition that AE is equal to V square divided by 4RL into P. But I am replacing RL by radiation resistance for maximum effective aperture, such that I can find the effectiveness ratio alpha to be equal to the ratio of AE to AE max, and the value of alpha lies between 0 to 1. This is the first definition. Scattering aperture or the effective aperture or the capture area, everything are one and the same, from which we have defined the maximum value also. The next type of aperture is called as scattering and loss aperture, defined by AS and AL. If it is AS, what is happening? For AS, the equation is I RMS square into, in the place of RL, we are replacing radiation resistance RR divided by P. So I can find out the scattering ratio, which is beta equal to, effectiveness ratio is alpha, scattering ratio is beta. It is just AS divided by AE. Next aperture is collecting aperture, denoted by AC, which is the sum of AE, AS, AL. We know AE is effective aperture, AS is scattering aperture, AL is loss aperture. In the basic equation of AE, we have IRMS square RL divided by P. In the place of RL, I am replacing RR for AS. In the place of RL, I am replacing R small l in the place of AL. So this gives the collecting aperture. So we have seen maximum aperture, effective aperture, scattering loss aperture, collecting aperture. And the other different concept of analysis is the physical aperture, denoted by AP. As the name itself indicates, it is related to the actual size of the antenna. So the physical size of the antenna it is related to. If the antennas are of larger size, for example, consider horn, parabolic reflector, etc. cases. In such cases, we say that the physical aperture is greater than the effective aperture. But in case of dipole antenna, the physical aperture is less than the effective aperture. Now, why are we speaking about this? We are speaking about an ideal size antenna with no thermal losses. Under no losses condition, we can say that the maximum directivity is achieved, which means that the effective aperture is exactly equal to the physical aperture. However, this set of equation will have an analysis in the continuation part. So the absorption ratio is defined by gamma equal to the ratio of AE max to AP. AP is the physical aperture, AE max is maximum effective aperture. It is physical aperture and effective aperture replaced. That's what is a continuation concept. So the relation between maximum aperture, gain, directivity. The radiation pattern, however, is same for both the transmitting antenna and the receiving antenna by analysis of reciprocity theorem. Let us consider two antennas A and B and their corresponding directivity, gain, aperture, effective aperture are defined as with respect to antenna A, with respect to antenna B. By gain and effective aperture correlation, we know that GOA divided by GOB is equal to AEA divided by AEB. We are not going into the depth of the analysis of how it is being proceeded with. So, by definition of directivity condition, we know that dA by dB is equal to AE A max divided by AE B max, which means that effective aperture maximum with respect to antenna A with respect to B ratio is equal to directivity of antenna A, directivity of antenna B. Now, in this equation, let us assume the antenna A is isotropic, which means that dA value is equal to 1. If it is an isotropic antenna, the directivity is equal to 1 is understood. So, I am replacing dA by 1. So, 1 divided by dB becomes equal to, right hand side remains the same. So, I can cross multiply these two equations to bring it to the form of dB equal to AE B max divided by AE A max. However, we are finding out the relation between directivity and AE max, for which case let us consider a short dipole antenna with AE B max value to be equal to 3 lambda square divided by 8 pi, and that of the directivity of the antenna B is equal to 3 by 2. So, I am going back to the equation AE A max, substituting these two values. Upon simplification, the equation is lambda square divided by 4 pi. Now, get back to the equation of dB. It is equal to AEB max divided by lambda square divided by 4 pi. So, upon simplification, 4 pi by lambda square into AEB max is equal to the value of dB. So, in general, I have replaced the antenna B as D itself. So, directivity of an antenna is equal to 4 pi by lambda square into AE max. This gets a relation between gain, directivity, effective aperture, the correlation. So, this gets a complete analysis of the parameter of effective aperture or the capture area or the effective area. Thank you.